Hello everyone, this is the fourth video on the SMO Junior mock paper which I've written. We'll be going through questions 16 to 20. Once again, if you have not actually seen the mock paper yet and you just chanced upon this video, do have a try. The link to it is in the description below. Let's get straight into question 16, which asks you to find the sum of all values x which satisfy this rather weird looking equation. This is an idea that I got from the Bay Area Math Olympiad actually in the US. It's kind of a nice question because you mainly need to notice one thing amidst all the chaos. And that one thing that you want to notice is that this is a linear equation. Now, remember what a linear equation is. A linear equation means that you just have something times x plus something equals to 0, or some rearrangement of terms that involve nothing more than either x or constants. You see that that's actually what happens here. And if it is a linear equation, no matter how complicated the coefficients are, there are only three possibilities. Either there is one solution, there are no solutions if it cancels off and becomes something like 0 equals to 5, or there are infinitely many solutions if it cancels off and becomes 0 equals to 0. Needless to say, this is not going to cancel off because the left side has a different number of x's as the right side. So it's not going to completely cancel off, meaning that there should only be one solution. Now, seeing as there's only one solution, what you can do is more or less just to try to guess that solution, because this is a bit too complicated to actually combine together. And you realize that it would be perfect if 7x equals to 2023. So if 7x equals to 2023, both of these are just going to become 1 over 1, 2 over 2 to 23 over 23, which is just going to be 23. And the right side would be 2022 over 2022, 2021 over 2021 until 2000 over 2000, which is also going to give you 23. So we're really happy with this. X is just 2023 over 7, which is 289. Now, from my experience, a lot of students are pretty angry when they see something like this. They say, how am I supposed to think of that? How am I supposed to solve a question like this? You mean I'm supposed to notice this works? Well, the answer to that is kind of in the question really. When you see something like this, asking yourself, how am I supposed to solve something like this, is really a good first thought, because it looks pretty absurd. Once you have gotten over that absurdity, the next thing is that it must actually have a very nice feature about it. And the nice feature is that it's linear, so there's only one solution. And for any question where they appear to have many solutions, but then you manage to guarantee there's only one solution to the equation, guessing it is perfectly fine, because you now know that as long as I find it, I know there's nothing else. So I don't need a systematic way to find my one solution, as long as I know that I won't miss out anything else along the way. Okay, question 17. What's the remainder when the 180-digit number 101112131415 until 97, 98, 99 is divided by 99? Now, for this question, you do have two different choices really. Now, one choice that might appeal to many of you is to use the test for 9 and 11. Right? To find the remainder when divided by 9, the remainder when divided by 11, and then put it back together again. Kind of like the earlier question we had about divisibility and remainders, we know that we can put it back together again. However, there is a faster way to do this using a little bit of modular arithmetic. And I've placed this question here because in recent times, the SMO Junior has tended to ask a question like this, where if you are aware of modular arithmetic, you can save yourself a huge chunk of time. let me just draw this for, well, more than one purpose, but it looks nice that way, right? Because these are all two-digit numbers in a block from 10 to 99. Now, I want to say that this number is actually going to be 99 plus 98 times 100, right? That's 9800, plus 97 times 100 squared, that's 97,000, and this continues all the way until 10 times 100 to the power of 89, right? 89 other numbers from 11 to 99 are now replaced by 00. So this is my number written in this form. If I take it modulo 99, 100 is congruent to 1 modulo 99 because their difference is 99. Now that means that you can replace all of the hundreds by 1. And so it is just going to be 99 plus 98 plus 97 all the way to 10. This I can calculate in the normal way really. It is 109 for each pair. There are 90 numbers and I divide by 2. So it's 109 times 45. And if I take modulo 99 again to reduce it, I can change 109 to 10. So 450 divided by 99, this one is just going to be 54 modulo 99. Yeah, so this is actually the same way in which you will be able to justify your divisibility test for 9. Except that instead of blocks of 2 digits, you only need 1 digit at a time. And similarly, if you have dividing by 999, you can take blocks of 3 digits and write it in a similar fashion. Next up, question 18. This is kind of an SMO favorite. You have got these square roots all over the place, which would be completely hopeless if not for the fact that down here, what we have are conjugates. Now, as you may be aware, conjugates are whenever you have a sum and a difference with the sign in front of the square root, the one that was flipped around. And the reason why we like conjugates is that if you add them up, you get something nice, and if you multiply them, you get something nice. Both ways, the square root gets cancelled off. So with this in mind, here's what we're going to do. We're going to square both sides, which is quite logical with the sheer number of square roots that are in the problem. Now, when you square the left side, you get x plus square root 1001. You get x minus square root 1001. And then you get 2 times their product. Their product is going to be just pushed into the square root like this. And of course the right side squared is 182. Now a few things that we can do. The first is the one on the outside is clearly going to cancel off the square root 1001. So that becomes 2x. Whereas on the inside, you can use your difference of squares expansion to say that this would just be x squared minus 1001. I'm going to divide by 2 first to make things a little bit nicer. Now remember what I said earlier about guessing an answer if you know there's only one? Well, at this point in time, if you felt like doing it, that would be perfectly okay. Right? If you wanted to try to guess what should your x be, you know that will work because as x gets bigger, the left hand side gets bigger and bigger as well, so there's only one value. But I'm going to do it systematically by first moving the x over and then squaring it again. So when you square it again, you get x squared minus 1001 equals to 91 minus x squared, which when expanded, you get 91 squared minus 2 times 91x plus x squared. So move things over, you get 2 times 91x equals to 1001 plus 91 squared. If you're looking at it quizzically, like, why am I refusing to multiply 2 times 91? What's so difficult about that? Isn't that 182? You're right, but because 91 is a common factor that can be cancelled off on both sides, so I didn't want to have to add everything up. Okay, so 1001 is 11 times 91. So this way, you don't have to calculate the 91 squared. Okay, so 2x is 102 and x is equal to 51. Now, the reason why we were not afraid to square it is mainly because, as you can see here and here, the cancellation we got from the adding up is the square root disappears. The cancellation we got from the multiplying is that the difference of squares gets rid of the square root. So from having 5 square roots in the original equation, after we squared it, we were left with 1. And we square it again after shifting things a little bit to get rid of that final square root. If you don't like square roots, neither do I. The square roots are not nice at all. And that's exactly how you solve many of these questions. You look for every opportunity to get rid of them as nicely as possible. Okay. Question 19. For how many integers n does this equation x squared plus nx plus 2022 squared equals to 0 have at most one real root for x? Now this is not asking you to find out what is x. This is saying that for some choices of n, you have at most one solution for x, meaning that either there is one solution or 0 solutions. How can this be? What I'm going to do is I'm going to first move over the 2022 squared to the other side. We get a negative number, but never mind. And essentially I want to ask myself, for what values of n is this negative 2022 squared not attainable? Well, for instance, if n equals to 0, this is not attainable, right? Because x squared cannot be negative. Now, if we did something like n equals to 1, would that be solvable? And in fact, if n equals to 1 or 2 or whatever it is, how will we actually go about trying to solve it? Now, we can't try to factorize something like this because, first of all, it doesn't say one integer root for x. And second of all, we don't really know what is n. How do we factorize it? So the alternative is certainly to complete the square. X plus n over 2 squared minus n over 2 squared. Okay, and then I will shift over n over 2 squared. Okay, so what does this mean? It means that as long as this side is positive, I'm going to get two solutions, right? Because x plus n over 2 can be plus or minus the square root of the right hand side. So the only way in which you can have one or no solutions is that this must be either 0, which gives you one solution, or negative, which gives you no solution. So that now changes it into a new inequality, which thankfully is not very difficult to solve. And at this point, we are very grateful that we did not try to square 2022 because that is completely unnecessary. Now you get n minus 2 squared is less than or equal to 2022 squared. If I multiply by the 2 squared on both sides, you get n squared less than or equals to 4044 squared. Now remember to read the question very carefully. It says integers. It does not say positive integers. So if n squared is less than or equals to 4044 squared, n is actually between negative 4044 and 4044. Right? Don't just say it is from 0 to 4044 or 1 to 4044 and forget the negatives. So therefore, you have 4044 positive, 4044 negative, and a 0. So the number of integers is 2 times 4044 plus 1, which is 8089 solutions. Okay. Last for this section is question 20. In the figure below, ABCDEF is a hexagon whose interior angles are all equal to 120 degrees. Suppose that CD is 20. Let's write it down. DE is 22, EF is 12, and FA is 36. And the area of the hexagon is n square root 3, find the value of n. Well, we're in trouble if we try to find the area of a hexagon by a formula because there's no formula for area of a hexagon, surely. What we do have is a very specific description of this hexagon. And the specific description is that they are all equal to 120 degrees. If you were thinking in the past that all 120 degrees means regular, you have a living, breathing example of a hexagon here where it is not regular even though all the angles are equal to 120. It's kind of like a rectangle, right? A rectangle, all the angles are equal to 90. That does not mean that it's a square. But we can find the area of a rectangle similar to how we find the area of a square. So we'll try to find the area of this hexagon in as nice a way as possible, because the 120 degrees give you a very nice property. If you were to extend this out, here, here, and here, you find yourself with an equilateral triangle because all of these angles are going to be 60 degrees. The exterior angles of your hexagon will all be 60 degrees. And that also means the entire triangle is itself an equilateral triangle. So that's really good because I can start to use all my lengths to label more stuff. This is all going to be 20. These are all going to be 12. And that means I know the side of the equilateral triangle. Right? 12 plus 22 plus 20 is 54. So that means that 54 minus 36 minus 12 is 6. This small triangle has length 6. And then 54 minus 20 minus 6 is equal to 28. So this length is 28. Now, so that's half the question done. The other half of the question is figuring out, then how do I get the area? And all of this comes down to, can I find the area of an equilateral triangle? So let's say that we do this in general for an equilateral triangle with side length x. Then, as we actually saw earlier, remember that we did the 30, 60, 90 triangle in a previous problem? We can say that this is in the ratio square root 3 is to 2. And of course, where this is half x, so you can use Pythagoras to get it back if you did not remember that value. And so the area of your equilateral triangle is half x times square root 3 over 2x, which is square root 3 over 4x squared. So that's the formula for area of an equilateral triangle, in case you have not seen it before. And so coming back to our problem, now all we need to do is to calculate the big equilateral triangle minus the 3 small equilateral triangles, which is square root 3 over 4 times 54 squared minus 20 squared minus 12 squared minus 6 squared. Okay, so I can divide the 4 off first to make numbers a bit smaller, right? Because 4 is 2 squared. So you get 27 squared minus 10 squared minus 6 squared minus 3 squared. Oh, come on, this is not a good time. I mean, the last few seconds. Oh well, okay, so we just need to calculate this. This is 729 minus 100 minus 36 minus 9. So this would give you an answer of 584. Because n square root 3 is the area of the hexagon. So for questions like these, if you are a little bit lost, try to avoid the temptation to randomly draw lines all over the place and hope for the best. Just slow down for a moment and think what would give you a nice way to calculate it. There is no formula for area of a hexagon, but when they are all 120 degrees, you can split it into some equilateral triangles. Alright, so this is all for the set of 5. We'll go through the last 5 problems in the next video. So thanks for joining. Please do subscribe if you haven't already, and see you in the next one.